So in the last section, section 3.2, we noticed that even though the waiting times of a couple banks were different, or were pretty close to the same, that something about them seemed different. So here was the waiting times for Jefferson Valley right here, and then the waiting times for, what was it, Providence Bank. So the difference was the second of these, Providence, seemed to be more spread out. And certainly a quick measure of how much variability there is in your data set is something called the range. And the range is just going to be the highest value minus the lowest value. So let me just type in range right here. And then we want to calculate that. So I'll type in equals, and then click the highest value. Fortunately, these are already sorted, minus the lowest value, which is an A1. So difference there is 1.2. So 1.2 minutes between the fastest and the slowest. That's pretty consistent. If I repeat that calculation down here, so again, the range equals the highest minus the lowest, there's quite a range here, 5.8 minutes. So, boy, you can get really stuck in these lines here. Even though the average wait time is about the same, you could really get stuck at Providence. Now, that's not bad, but it's not a real good measure of the complete variability because it only involves two values. Thank you. I mean, maybe it's just, if I add just one more value here, maybe I can put in a 17.7 that something happened, etc., then the range here could really explode, even though there might not overall be that much variability in the data. So we want to create our own measure of variability, something a little bit better that involves all our data. So one possibility here, and let's see, I want to get rid of this, I guess. One possibility would be to take and subtract off the mean wait time for all of these values. So let's find out what that average is. Let's see, I'm just going to type over this. Average. Let's find out the average here. So the average of this column data is 7.15. So I'm going to take and subtract off that average from all these pieces of data. So equals this minus 7.15. Whoops, how come I'm getting a false there? Oh, thank you. Equals here minus 7.15. Thank you. And I want to do that for all of my data, and I'll add it up. Find out, what that difference is like. This would be how far spread out our data is from its center. So come down to here and click sum. We want to sum up those differences. What do you think is going to happen? What am I going to get? Any predictions? 0. Wait a minute. That doesn't sound right. Really? If you actually did it again down here with this data set, you get the same result. So if I subtracted the mean, in this case it was 7.2, so equals, and you don't have to do this, but I will demonstrate it, 7.2. If I did it here, and then added up all the data, or added up all those differences, again, I'm going to get 0. It's always going to happen. So using this as a way to talk about the variability is not very good because I always should have got a 0 here. Why didn't I get a 0? Is it 7 point? No, this one was 7.2. I must have made a little typo someplace in typing these in. 4.2, 5.4, 5.8, 6.2. Is it 7.15? Oh, okay. Let's see, 7.15. Let's copy this down then. Okay, yeah, that did it. All right, so using that as a way to measure the center or how much variability there is just doesn't work because you have all these numbers that are above the mean and all these numbers that are below the mean. When you add up their differences, they add up to 0, always. You can show that that's going to be true mathematically. So the problem is that some of these are positive and some are negative. One way around that is to square these numbers so that you get rid of the negative part of it. So I'll do that in this column. I'll type in equals, then click over here in the column B1. If you hit the shift key and then the 6, you should get an up arrow and square it. If we square these values, then they're going to be positive. We won't have to worry about them adding up to 0. So I'll square that one, and I'll do likewise for all these values here. Now when I add this up, I'm certainly not going to get 0, am I? I can't get 0 because these are all going to be positive values. There's still a problem with this though. The problem is that no matter what you do, when you add more data, this number is going to grow. So rather than looking at the sum of the squared deviations, we're going to have to be a little bit more clever. So let's take stock of where we're at here. We've taken our data. So those are your data values, x, subtracted the mean, and squared it. Okay, but like I said, when you add more pieces of data, that total is just going to grow and grow and grow. So to use that as a measure of variation is not such a good thing. So we're going to calculate kind of an average. We're going to take this total and divide almost by n. It's by n minus 1, and that's going to be for us the sample variance. N minus 1, n is the number of pieces of data involved in your calculation. So this is the variance. So n is number of observations. So let's see what that would do. So if I come back here, I had 10 pieces of 10 data values. So I'll take this one. So actually, you want to click an equals down here. Equals this divided by 9, and that gives me the variance. So that's your variance. Of 0.2272. Now, if I did the variance calculation down below for the other set of data set, or for the data set below, would you expect it to be bigger or smaller? Is there more variance in this data or less than the first bank? Yeah, this should be a bigger number. I'm sorry, there's a question in the back? I'm calculating kind of the average. If I was exactly calculating the average, I'd be dividing by 10. But it's a nice observation that we're not exactly dividing by 10. We're dividing by 9. The reason goes a little bit beyond this class, or it makes this what's called an unbiased estimator. I'd like to talk about that a little bit more later, but it just works out nicer to make this a better estimate of what we want to try and get to, which is our population variance. So it's a good question. We can definitely return to that. Not to be the bearer of bad news, but there's still a problem with this unit. And that is, if you were starting out, well, our data started out in wait times, then by doing this calculation, we've got something that measures things in wait times squared. So it'd be 0.27 minutes squared, which isn't really the same as our original units. So if I want to get rid of the fact that I've got a square unit, what's going to unsquare things? What's the opposite of squaring things? Square root. So here's our final calculation. S is going to be the square root of the sum of x minus x bar squared over n minus 1. And this is the sample standard deviation. And we will use this a lot. So you take the difference between your data and the mean, square it, add up all those square differences, divide by n minus 1, and then take the square root of the whole thing. Now there's ways to make this an easier calculation if you're doing it by hand, but the good news is we're not doing it by hand. So let's go back to our spreadsheet here. If you were to take the square root of this, so equals, let me just take a guess, SQRT, square root of this value, then that should be our standard deviation, assuming we've done our calculations correctly. So STD, dev. There's more good news for you. I'm not going to make you do this by hand. And realistically, we didn't really do it much by hand. We did it on a spreadsheet. Let's go down and find these numbers for this data set and be a little bit more sophisticated about it. We'll type in equals and then variance. Let's click this. And then we can also do the standard deviation, STDEV. So equals and then standard deviation here. This class is not about you doing these kind of calculations by hand. When I started teaching this class back in 19 mumble, people did this by hand. I made them do a problem on their exam by hand. We've got better technology available to us now, so we're done with that. Yes, sir. That's a great question. I haven't exactly figured out what I want to do about this on an exam, but I'll work on it. Yeah, that's my problem to deal with. One of the things I want you to be able to do, though, and this wouldn't require any calculation at all, is interpret this stuff. And that's really what your job as a statistician is going to be. I mean, computers can come up with the numbers, but your job is going to be to explain this to somebody who doesn't have a statistics background. I mean, if you did a study like the one we just talked about life expectancies in the U.S., and you said, well, we rejected the null hypothesis at the 5% level that the mean life expectancy of women now is greater than it was for their daughters. Wow, what does that mean to the layperson? You've got to put that in words that somebody understands. So a question that I could ask you here would be, all right, here's the standard deviation for two data sets. Which one has more variability and why? If I give you the standard deviation for both of these, you say, oh, well, the higher number reflects the higher standard deviation. So this one has more variability. That would be the kind of question that I could ask without necessarily making you grind out a bunch of numbers or log on to Excel. So, does that answer your question? Okay, good question. Thank you. Appreciate it. A couple things about standard deviation. Standard deviation reflects how spread out the data is. What's the smallest that you could think of that the standard deviation could be? How small do you think it could get? 0. Standard deviation always has to be at least 0. In fact, there's only one circumstance in which it could actually equal 0. And that is if all the data were the same. If all the data were equal to the mean. And in that case, you would get a standard deviation of 0. Anything else, standard deviation is going to be greater than 1 or greater than 0. So, yeah, like I said, one last thing to note is that the standard deviation should be greater than 1 or greater than 0. S is greater than or equal to 0 always. Okay. Tell you what, let's do a couple more here to finish this one. Work on finishing this section up, and then I'll give you guys a break. Let's move to problem number 8. All right, so the National Highways Traffic Safety Administration conducted crash tests of booster seats for cars. Listed below are the results from those tests with the measurements given in HIC, which is your head injury criteria. According to safety requirement, the HIC measurement should be less than 1,000 HIC. Do different child booster seats have much variation among their crash test measurements? Well, what's your eyeball test of this give you? Yeah, it looks like there's a lot of variability. I mean, you're going from 431 all the way up to 1210. So let's actually find that variability. So we'll put those numbers into data set. And I'm just going to clear out all this data here. So I'll delete it. Oops. Yeah, I got everything. And let's enter in the new data set. 774, 649, 1210, 546, 431, and 612. So we can find a couple things pretty quickly. We can find the average. So let's find the average of this data set. And let's also find the standard deviation. Standard deviation, STDEV. Wow. Sure beats doing that by hand. Nice and quick. If you were in StatDisk, Explore should give you more statistics than you know what to do with. But let's take a look at the standard deviation here. 272. Well, it's tough to say if that's big or small until you start comparing that to the sample mean. 272, that's pretty big compared to the sample mean, isn't it? That's like almost 40% of the sample mean if you just do a quick calculation of one divided by the other. So, yeah, there's a lot of variability in this data. And in particular, one of these, I don't think I'd be letting my kids ride in. let's talk about something called the range rule of thumb. Oops. Not what I wanted. There. This shape of a data set, of a histogram, should look familiar. What did I call this shape the other day? Yeah, bell curve. Has a normal look to it. So oftentimes, if your data has a normal shape, then the data has a range. Most of your data is going to be within 2 standard deviations of the mean. This is starting to give us a little means by which you can tell what's usual, what's typical about your data, and what's atypical. If you're outside of 2 standard deviations from the mean, that's starting to reflect an unusual value in one way or another. Most of your data is going to be within that 2 standard deviations of the mean. Now, that gives you kind of a way to estimate the standard deviation sometimes. And that is, if you take and were to solve for S in this equation, that is the range divided by 4, that gives you a rough estimate of the standard deviation without actually going through all that calculation. All right, we're going to break this up into two segments. Let me give you a break here. We'll come back and finish up section 3.3 in a few minutes.